It is our great pleasure to see you again after 2 years of break at this spring meeting, and that we are again able to offer you a program that has a variety of different topics that might be of interest for you. And to start with, we will focus on a topic that I think everybody has excited over the last weeks and months, the James Webb Space Telescope, empowering science through partnerships. And it is my great pleasure to invite on stage the moderator of this session, the president of the IAF, Professor Pascal Ehrenfreund, who will also introduce the speakers. Pascal, please.
Yes, thank you very much. It's wonderful to start up this nice afternoon with such an exciting topic. It is the world's largest and most complex space science telescope which was ever built. And we will hear from experts today about engineering, science, and international cooperation, and what kind of mysteries this telescope will actually solve in the future. So I just want to introduce very briefly the speakers of this panel. Mr. Paul Geithner, the Deputy Project Manager Technical for the JWST project from NASA Goddard Space Flight Center. And I think he has also worked for the Hubble Space Telescope before, yeah? And Mr. Markus Kissler-Patig, Head of the Science and Operation Departments from the European Space Agency. He's an astrophysicist and will be able to answer you all the scientific questions about the James Webb Telescope. And Mr. Steve Iris, a Canadian permanent delegate to the European Space Agency, Counsellor of the European Space Affairs and the Embassy of Canada. I take it here in Paris. Yes. Wonderful. So we have also really different aspects which we can ask, and you can already prepare your questions. It's really for a diverse audience, and it's really an amazing project. And I think all of the panel members also have PowerPoint presentation to share with you. And I'm going to ask Paul Geithner to be the first one. Thank you.
All right, is this working? Yes. It's my pleasure to be here. Thank you, Pascal. All right. So what is Webb? Webb is a deployable infrared observatory with a 6.5 meter diameter aperture, 25 square meter filled aperture, an adjustable primary mirror because it's segmented, and 165 square meter sun shield, which is in 5 layers, so it's actually over 825 square meters of sun shield membrane. It's at cryogenic temperature for background limited infrared performance. It was a Christmas gift to the world. It was launched on December 25th on an ESA supplied Ariane 5 ECA rocket. We received a perfect launch, and we are now at Sun-Earth L2. And it was a quarter century in development. We're in the middle of a 6-month post-launch commissioning period, and it has a 5-year minimum duration science mission, but we hope that it will operate much, much longer. So NASA Goddard Space Flight Center, which is where I work, we are the mission lead, but our international partners are ESA and CSA. And the major US contractors were Northrop Grumman, Ball Aerospace, ATK, and L3 Harris. There are 4 science instruments aboard the observatory, a near-infrared camera that was led by Marcia Ricci at the University of Arizona, built by Lockheed, a near-infrared spectrograph, which comes from ESA and Astrium. It's the workhorse spectrometer on the telescope, a mid-infrared instrument that was provided by ESA and had JPL participation. Rutherford Appleton Labs was a major piece of that. And then the fine guidance sensor from Canada, and also has a science instrument part, which is the near-infrared the spectrograph. ComDev was the major contractor there. And of course, the Space Telescope Science Institute, with support from ESA and CSA, is performing ops. So just a few characteristics as an overview. It's a large telescope for resolution and sensitivity. I think as many people know, size is important with telescopes, and we need a telescope this big to do the science that's required of it. The telescope and the instruments are extremely cold. That's so that they don't see themselves. This is for infrared sensitivity. It's a multi-layer sun shield. A 5-layer sun shield separates the sunny side of the observatory from the shaded side, as opposed to a tubular light baffle, which a lot of people are familiar with and what Hubble has. And that's to provide shade for the telescope. It also is a design that allows the instruments and the telescope to passively radiate their heat to deep space and get cold passively. And when I mean cold, I'm talking temperatures below 60 Kelvin, so that we're limited by the infrared background that's present in the inner solar system from the zodiacal dust. It's folded up for launch, and we unfolded it in space for operations. It has to be so large. It's so large, driven by the science, that it was too large to launch in its operational configuration. Plus, it wouldn't have handled the loads of launch, so it had to be folded up. But that meant it had to be unfolded in space. So we call it the origami observatory, and that was some of our biggest challenges in building this thing. And then lastly, its location about 4 times farther away than the moon, on the opposite side of the Earth from the sun. That's so we can get it away from the room temperature object that is the Earth, and then enable sensitivity and observing efficiency. So the science themes, which Markus can certainly talk more about, originally this was conceived as something to see the very first luminous objects in the universe. They emitted their ultraviolet and visible light so long ago that that light has been redshifted to longer and longer wavelengths by the expansion of space itself since the early days of the universe, such that it arrives to us today as infrared light. And that's why, if you want to see the first visible light to shine in the universe, you need an infrared telescope today to see it. This is originally what we designed Webb to do. It will also look at galaxies over time, how they evolved and how the universe got from its early days to today. It's also an excellent machine for studying star birth and death. And finally, exoplanets, which is a new field of study that didn't even exist when Webb was conceived. And I know Markus can talk a lot more about that, but Webb will be a particularly powerful tool for studying planets around nearby stars. And why we're really here, this is a product of the United States, Europe, and Canada. Collaboration enables the partners to achieve more than they could on their own. And scientists all over the world share the same objectives. Astrophysicists in Europe, Canada, United States, wherever, they all have the same questions, want the same answers. And so pooling our resources, we can do more together than we can separately. The keys to success, as I've found them as an engineer and a project manager, is close engineering collaboration. And to really enable that, we need clean interfaces, and that's so that we can have that close engineering collaboration within the statutory frameworks, especially in the United States, that prevent us from sharing every single little design detail, even with our close friends. And then how the partnership originally was sort of constructed was so that the coin of the realm in operations is how much time scientists get on the telescope. So there was some legacy from Hubble where 15% of the time is guaranteed to be allocated to European scientists. So the deal was, all right, ESA, if you can give us roughly 15% of development contribution, that's proportional, then that's proportional. And the same with CSA with 5%. So. And that worked well on Hubble. I anticipate it's going to work really well on Webb. So what's the status? We're halfway through commissioning. It's a 6-month commissioning period because we had to deploy the thing. Very complicated. 344 single-point failures. 295 of them were associated with the deployments. When those were done within the first 2 weeks of launch, many of us breathed a sigh of relief. A lot of risk of the mission was retired at that point. The telescope is aligned as I speak, and the optical performance is spectacular. One of our top performance requirements was to be diffraction limited at 2 microns. I can tell you that we're diffraction limited at closer to 1 or 1.25 microns. It's outstanding. We're ecstatic. We're almost fully to operating temperatures. The last thing to get to is operating temperature is the mid-infrared instrument. Since it sees mid-infrared light, it uses arsenic-doped silicon detectors that have to be below 7 Kelvin to work, and the effective sink temperature of deep space at L2 is 7 Kelvin. We're not going to get there by passive means. So we have a cryocooler on board that is currently chilling MIRI down to this temperature, and in about 8 or 9 days, we'll be down below 7 Kelvin with MIRI. And then lastly, the science instruments, they've all been turned on. We're taking darks with the instruments. We're beginning to calibrate them. They should all be ready to perform very accurate science by summertime. And this is my last slide. And you'll see this beautiful engineering image of a star we use to align the telescope. And you see the 6 diffraction spikes from the hexagonal shape of all the mirror segments, and then the faint horizontal diffraction spike is from one of the secondary mirror support structures. But we can't take an image for engineering purposes without seeing almost uncounted numbers of galaxies in the background, and the scientists are just salivating. And as an engineer and as a backyard astronomer, I am stoked. And this is a wonderful observatory, and can't wait to see it do science here in a few months. And with that, I'm finished, and thank you.
Thank you very much, Paul. I just wanted that you repeat the number of single-point failures. How much?
344,
okay.
Which we've retired most of them. The ones that remain are sound like a lot, but they're actually pretty standard for a spacecraft. But yeah, we retired quite a few with all those deployments.
This is quite amazing, yeah. Thank you very much for this interesting insights. And now we are coming to Markus Kissler-Patig from ESA, who will discuss a little bit more about the science goals.
Yes, thank you very much. Good afternoon, everybody, and thank you for the invitation. Nice to be here. So my name is Markus Kissler-Patig. I'm the head of science and operations at the European Space Agency. So we, in my department, are responsible for the operations of all the heliophysics, planetary, and astrophysics missions. And so the scientists and engineers who from ESA side work on Webb are under my responsibility. Just a word for the last image that Paul showed. It was for me a double wow image, because I first saw the quality of the PSF, so the point spread function, which was amazing. So, absolutely, we could have kissed the engineers for delivering us such a good image quality. But then the second wow was to see all the galaxies in the background. It's like, wow, dude, let's start doing science. And of course, we have to wait still a little bit. So I just wanted to make 4 quick points, meant as a teaser, and then happy to take any of your questions on any of these. And these are really a little bit the ESA contribution to this amazing mission. So we feel extremely privileged to have been joined as junior partner here in NASA and be participating in this mission and opening actually this most powerful telescope humankind ever sent to space, also to the European scientific community. The launch was probably the most visible contribution. You probably were in front of your, or hope you were. Certainly I was in front of your TV screens on Christmas afternoon here or lunch actually on this year, and saw this launch. I think there's an animation. Maybe it plays, maybe it doesn't. Let me try that again. No, so let me go back. Okay, so but here we had to actually work in close collaboration with our colleagues to actually fit the folded telescope into the fairing of an Ariane 5, which is of course the kind of workhorse launcher for Europe. Over 100 launches since over 20 years. Nevertheless, it was nerve-wracking. I had nightmares of what would happen if NASA screwed that up, so the relation between ESA and NASA would have probably taken a long time to repair if we had made a mistake there. So thank you very much to Ariane Espace and all our colleagues here. The other amazing for me part of the launch was it was so precise that we extended the lifetime of the observatory. So there's fuel on board. The fuel is actually meant to correct the trajectory in case the launch is not perfect. But this launch was so amazingly perfect that 2 things happened. A, very little fuel is needed on the way to L2, I mean on the first months on travel there, which means that you have a lot more fuel to actually retain the on station, the observatory there. So instead of actually aiming at 10 years, we're now fuel-wise looking at almost 20 years. Other things might have a shorter lifetime. We hope that it was over-engineered and that we will see Webb lasting as long as Hubble, so for 30 years. But we know at least now that there's enough fuel, and we trust our colleagues engineers to actually find ways to save even more fuel and last it longer. The other thing which was so amazing is that the launch was so perfect that on this selfie camera that we had on board, you could even see the deployment of the solar panel on the images, which we didn't expect to, which scared me because I didn't exactly know what it was. Paul told me he knew exactly what it was, and he was wow. And that was another fantastic moment. So the launch went as well as we could hope, and the following days, as Paul just mentioned as well. Instruments was another big contribution from the European side. There are two instruments that we contributed. NIRSPEC, which is really the workhorse instrument. It's the one here on top, which I would have said is a pure European contribution, but nothing is. It's all collaboration. So in fact, we got the detectors and the microshutter arrays from Goddard, and the know-how of Europe for this type of spectrographs. And it's a spectrograph which allows you to actually take spectra of 200 objects at a time. So of course you save a lot of time instead of going one by one, and will really allow us to discover the far universe. And then MIRI, which is the instrument which pushes really the limit into the furthest infrared that we have on board. As Paul mentioned, it's the one when you observe at these wavelengths, you need to actually cool the instruments even further down at just 8 degrees Kelvin above the absolute zero. That's the only one that we need to actively cool, so it's being cooled at the moment. Everything goes well. All the other ones are passively cooled. The third point is science, which is really what I'm living for, although I have little time for it at the moment. But the early universe was, I was part of these discussions on what to push the frontiers next 20 years ago, and we wanted to actually learn how our universe is created, what structure formation is, how galaxies are assembled. We knew that in order to actually look far, because the universe expands, light is actually stretched into the red. And with a telescope such as Hubble, which observes in the optical, you are limited in how far you can look back. When you actually go into the infrared, you can actually push back even further to the really beginning of the structure formation in the universe. And that's what Webb is going to do. And so we learn a lot more about how we came to be, the big picture. But now when you're in the infrared light, you can also pierce through the dust. And so it allows you to open a lot more other science fields that are very interesting, which is the life cycles of stars who are born in dust cocoons, but also because in that infrared light you have all the molecular absorption. It allows you to actually study atmospheres of all kinds of objects, planets in our solar system, and make further progress there, understanding our neighborhood in a sense. But also because we, in the meantime, in the last 20 years, the field of exoplanets exploded. We now know over 5,000 planets beyond our solar system, and Webb is fantastic to actually study them and characterize the atmosphere, understand whether we're unique, whether the solar system is unique, and how we go from there. So really very, very excited, exciting science coming up. Just as a reference, these are Hubble images on the left in the optical, in the right in the infrared. So it gives you a little bit of a feel. This was with WISCAM 3 on Hubble. It gives you a feel how you can pierce through the dust really once you're in the infrared. And Webb has a collecting surface, so a surface which you collect photons, which is about 10 times larger than the one of Hubble, which makes it 100 times more sensitive. So we'll be able to actually pierce through the dust as we never had a chance to do with Hubble. So really a lot of exciting science ahead of us. So the last and the fourth point I wanted to make was about collaboration. Of course, there was a great story of collaboration between our space agencies. That's really, I think, the main one. I wanted to highlight also how in Europe, actually, both the industrial partners and the public sector collaborated to make all this European contribution happen. So I have here a slide, but I'm not going to actually go through them because it's really a very large number of collaborations which happened to make this mission also happening from European side. And last but not least, this is as exciting as all these last 20 years were, probably the most exciting ones for engineers with the next few months to come. Starting this summer, we'll do real science with it for the next 10 to 20 years. And that's where even more collaboration will happen. This is a map, an overview of the accepted science proposals in Europe. But most of these proposals are actually international collaborations. So very often, actually, for most of them, there are Canadian, North American, US collaborators on these proposals. And it's really there where we'll see also, as we saw on Hubble, this international collaboration kicking in, all these international ideas and pushing really the knowledge of humankind to the next level. And that's what we're, of course, super excited about. So I'll end here with my part and hand over to Steve.
Yes, thank you.
Thank you very much. Good afternoon. So on my side, I'll focus on the Canadian part and the Canadian role in the exploration of the universe. And as you can see by my title, I'm not as detailed in the knowledge of this famous and wonderful project that is James Webb. I'm sure I can cover some of the elements that I learned a lot about the last few days and weeks about this great project. So in terms of James Webb, what I'm really pleased here is to see the Canadian Space Agency logo alongside with ESA and NASA one. We have a very long-standing collaboration with both agencies for many decades in different projects and different topics. We have very strong expertise in astronomy and engineering and science in Canada, and the fact that we've been recognized for that and being part of this amazing project is very important for us, and it's bringing a lot, as you can see a bit later on. You mentioned about the trust of ESA, NASA and ESA to launch this wonderful instrument. Is the same on Canada's side, as there's an important part of this system that has been attributed to Canada that's clearly important for the operation of the telescope. Oops. Let's move on. So, okay, what have you contributing? So there's two instruments. They are installed on the same hardware equipment, but they're two different and operate independently. So there's the fine guidance sensor and the near-infrared imager and slitless spectrographer, so NIRISS instrument. So the main one that I just referred to is really the fine guidance sensor. So this is really what will point on the star we want to look, or the object we want to monitor, and we'll keep the focus on it, and will be stabilized to be sure that we have the clearest picture as possible. And what it's doing is that you focus on the guide star, and after that, if I understand well, you correct me if I'm wrong, eh? And every 16 seconds, it will move to be sure that it's correcting, so it's stable as much as possible, so it don't move. Because my understanding is that it's not a full stable infrastructure, so it needs to be corrected regularly, and that's why we'll have a clearest picture. It's used right now for the calibration part, which is really important for the commissioning, and will be used for all the operation function after. In terms of the other instruments, so the NIRISS is really designed to work on the distant universe part, the initial galaxies that appear shortly after the Big Bang. The other part is that it will be also to measure the thin atmosphere of the stars that we can, or planets that could orbit distant stars, that will be used for exoplanet discovery if we are able to detect some of the spectrum elements like water, carbon dioxide, methane, and others. That is usually indication that could be potentially supporting life or help to discover exoplanets. So what it brings to us in Canada, as referred to, we have access to observation time on this wonderful telescope. So 3 of the phases, so the early release science, the guaranteed time observation, so we have 450 hours that will be guaranteed on observing using NIRISS or other Webb's instrument on it. And there's also the general observation, the 5% that have been referred here by Paul. There's already the first cycle that have been done. We have 24 projects that will be supported financially by the Canadian Space Agency. I think this is all of them that have been requested funding from us. It's not major amount, but at least will help to do some science and support some development. the main two leads on the science team, so Professor René Doyon from the University of Montreal and project scientist Chris Willett from the Canadian National Research Council. Here on the picture, there's also a representative from NASA and Honeywell. So Honeywell is the company formerly known as ComDev Space Inc. before. CSA fund all the instrument and also the science that will go after. And it's also a contribution of different universities and institutes that also part of the Canadian science team. You have a list here. It's not only in Canada, there's few that is coming from the US also. So, in a nutshell, Webb is the most complex and powerful space telescope ever built. I think you have already have a good presentation before by both my panelist colleague here. Canada has contributed a scientific instrument and a guidance sensor, which is a clear main instrument of importance for the operation. And Canadian scientists will take part in Webb exciting science mission that promise to change our understanding of the universe. So we are very stunned already by the early images that we receive, but we're just expecting even more in the later on. So, like I mentioned, international collaboration is not only on the development of the space telescope, but also after, when there will be data and we can work on it, that will bring also other interesting international collaboration. So on this, thank you very much.
Yes, thank you very much to all the panel members for this overview. And I'm sure that the audience is now collecting questions. And until they do, I wanted to ask a few questions and start with you, Paul. You have said we are halfway into commissioning. And I think a lot of people are amazed how is it possible to have such an incredible complex mirror with 18 segments being deployed flawless. I'm not sure if it was completely flawless. I think we would like to know more how were the last 3 months, how will be the next 3 months until the telescope will be really operational for science.
Sure, okay. We have to pinch ourselves because it really has gone pretty much flawlessly. And that's not by accident. That's the work of a lot of talented people over years and years and years around the world. A success like this doesn't happen by accident, so I've got to give props to all the engineers and scientists that worked so hard on this for so long. Well, the first 2 weeks were very hectic because that's when we're deploying everything. The size of this thing, as I mentioned, required it to be folded up for launch. So on the ground, when we were building this thing, every time we tested the deployment, we had to refold it, and that was almost like a complete reassembly. So that's part of why it took so long, is you're almost rebuilding this thing. When we deployed the telescope at the observatory level, it was 3 times. So it's almost like assembling the whole thing 3 times. And deployments in space are hard, but deployments in space of floppy things are absurdly hard. So deploying the telescope actually wasn't that bad because it was all rigid structures. There was a tripod that came out for the secondary mirror, and the outer 3 of the 18 segments folded out like the leaves of a drop leaf table. And these were on deterministic structures. But the sun shield, which is necessary for us to achieve the temperatures we need, and it's 90 cables totaling about a quarter of a mile. Okay, so 0.4 of a kilometer in length. As I mentioned, 825 square meters of 5 membranes that are 25 microns thick. They want to go where they want to go in space, and you have to control all those cables and all those membranes deterministically. So we didn't have any more than about 40 or 50 centimeters free lengths of anything during deployment, so that nothing could snag or tangle on anything else. And the design of that and the testing on the ground of that, and then finally the deployment in space of that, was an incredible engineering challenge. And that it all worked flawlessly, and it had to work flawlessly, is just amazing. So that was the hard part for deployment, and that was 2 weeks. The mirrors, that's a whole nother kettle of fish that wasn't easy, but was fascinating. So the 18 segments they're launched retracted about 13 millimeters against hard stops from their nominal position. So once the sun shield was out and the telescope rigid structures themselves were out, we had to deploy each of the 18 segments 13 millimeters to a nominal position. And then they're all somewhat randomly oriented. They point wherever. So in our first image, we were looking for 18 different spots of the aberrated spots of the same single star. And so the process goes through, you take that first picture, you're looking for 18 images, and right away we found 18 images. They're all over the place, but we found them. So we knew right away that things were looking really good because they weren't that badly aberrated. Then we organized, we identified, we moved each mirror segment a little bit at a time, so we knew which image went with which mirror. So once we did that, we arranged them in a pattern that looked like the telescope, an array of 18. Then we adjusted in all 6 spatial degrees of freedom the mirrors so that they made clean images. And we also were able to adjust the amount that each segment is cupped. So there were 3 that we needed to make really minor adjustments to on their shape, the figure of the mirror, and they came in beautifully. Then we stack all 18 of those on top of each other. I'm almost done. Then we stack all 18 on top of each other. Then we get them all in phase, so they can be out of phase by wavelengths of light, and you can get fooled by that. It's like, are they all actually the same surface, or are they one wavelength, integer wavelengths of light apart from each other? We got them all so they were all on the same surface, and then we fine phase them. And it's a process where you look at images and you come up with a mathematical solution, deconvolving those images, and then you know what to do to each segment. And as Steve mentioned, as Markus mentioned, he was ecstatic when he saw the point spread function. We were too. Believe me, we were getting such wonderful point spread functions. Like I said, our total wavefront error budget for the telescope, so it's as good as nature allows, which is what diffraction limited is, right? Because light is a wave, it diffracts. It doesn't. You put it through a hole and it spreads out. So a telescope's a hole. So we diffract the light, and if all our imperfections from building and aligning the telescope, if they're perfect, you still get a somewhat fuzzy thing, and that's called diffraction limited. I'm dumbing it down, but that's kind of what it is. So at 150 nanometers of total error for everything we built and aligned on the telescope, we're diffraction limited at 2 microns. Well, we're diffraction limited more like at a micron. And it's wonderful. It's going to enable even more science than we're going to enable already. So sorry for the really long answer.
No, I think this is...
That took almost as long as it did to line the telescope. I apologize.
I think this is the really, yeah, thank you. You know, this is a community which is fascinated by these things, and I think you really explained that very well, how amazing that is. I don't want to monopolize. If you have any questions, we have our secretariat with microphones. Please just raise your hand, and in the meantime, okay, we have only this. Okay. Okay.
I want to warm up the audience. I know that they are shy to ask questions. Okay. No, I'm joking. No, I'm just very curious. I know we are preparing for the IEC in Paris in September. And of course, everybody will be very curious to see what's your expectation, what could be already presented in September at the IEC as the first results of James Webb.
I can answer that. So the... something which was, to me, very nice was decided for the Webb telescope. So we'll have to wait until the end of commissioning, which is going to be around July. And then there's a set of what we call early release observations. So there was a call out and the most interesting ideas. And typically, as you know, we try to protect intellectual copyright in a sense. So astronomers who propose observations You usually have 6 months or a year of proprietary time to actually look at them. For the early release observations, there's 0. So these images will be taken quickly and actually be jumped on by the entire community. So I'm sure that 12 hours after we release these images, you will see the first scientific, or maybe faster even, right? So I know of people who already have written the papers and just need to put in the numbers. The targets are known and so on. So I'm pretty sure, but by September we'll have a book to present probably, right? So because scientists are so eager, so and these are spectacular images. I mean, really from images, and we'll see them. I think it's molecule that are just beautiful. I mean, just for the inspirational beauty, but already with all instruments, we'll see results, also spectroscopy and hard science results, and when you open parameter space, when you start to push, a factor 100 in sensitivity, almost everywhere where you point is breaking through new ground, and so there's going to be discoveries immediately by the flock. So my prediction is that by September you'll be able to have some presentations of amazing science right away.
We will be very happy. Yeah? I just wanted to ask a question to Steve, because you mentioned that the international cooperation is amazing. How this really complex telescope has been built, sent into space and be deployed. But it doesn't stop there. It is this data analysis which will happen in international cooperation. And can you tell us a little bit more about it? How is this international cooperation designed? Of course, you write proposals together, but has Canada, for instance, special interests, and entities working all over the world on particular topics, particular with its instruments?
Yeah. Without going in the detail, because I'm not aware if there's specific priorities they're looking for, but usually when we have call is for the funding is done for Canadian astronomers, but usually they are very encouraged to partner with others, and usually they gain point when they deal with other entities, especially at the international level. But by default, it's usually what is happening in the case. So the ERG have established collaboration at international level. It's not only in astronomy. I can say that mostly in science this is the case. Probably more even on astronomy, but on our side we don't have. Usually the funding goes for Canada at the first, but they're usually encouraged to go with partners. But I'm sure that they will work with partnership internationally under that aspect. So we're focusing kind of on 2 elements. So there's the industrial part, which is kind of important for us, and we see it through that project. This is interesting. It's collaboration not only in the engineering side to develop that system that bring interesting collaboration. As I mentioned at the beginning, is the part of all the collaboration that bring even more results. But there's also what we're looking at is really the number of years after will be part of the collaboration. And we see that for previous project that we have supported in astronomy. So even our small, very suitcase MOST telescope that had been launched 20 years ago that we call the Hubble telescope, because it was very, very small compared to Hubble, bring a lot of international collaboration. And so I'm sure that we'll see it. But to specifically identify a priority where Canada will look at, I'm not familiar enough with the question, but I can bring back with the information I need.
So there's one aspect which I really, really like on Webb in terms of international scientific collaboration. I've worked in my career on many different projects which were international collaborations or institute collaborations, and typically the partners divide the time among themselves very strictly, and they have their own actually time allocation committees. So you know that we allocate telescope time according to the merit of the idea. And usually partners really try to actually isolate themselves and do that. For a project like Webb, as for Hubble, we really decided to have only a single time allocation committee. So really all the partners joined and said, let's actually really get the best ideas executed here. Forget about the exact shares, and they will work out more or less, which they do at the end. Okay? But it's, I think, it shows the collaborative spirit which is behind that, the fact that the partners trust each other and that they're really trying to actually get the best science done as opposed to actually protect territory. And that's not trivial, because really most of the projects I work with try to defend their turf. And I'm so glad that actually Webb is a lot more open-minded and in this true scientific collaborative spirit does a single time allocation committee. Yeah.
And I should note that you know, I mentioned the 15 and 5% guaranteed, but if Hubble is any example, and if cycle 1 is an example for the future, more than 5% and 15% respectively are won on merit by our partner agencies, but scientists from our partner groups. So it's a great story. Yeah.
I have a question about new worlds. So with the performance that you have, so will you have enough stability of this point spread function that eventually you could even go below the resolution limits, for instance, to image solar systems? So would you be able to detect from Proxima Cent the solar systems ourselves, the different planets that we have? And then you could describe also how we could detect atmospheres in this other world with the transit spectroscopy.
So without going into too technical details, so yes, so the fact that actually we are diffraction limited not only at the requirements 2 micron, but actually pushing it also to 1 micron. The shorter the wavelength, the harder it is to actually make your optics so good that actually you still reach the natural limit of the optics. When you look for exoplanets, you're really trying to actually look at the contrast. So it depends, of course, on how big your planet is and how far away it is from its parent sun. But contrasts between the star and the reflected light from the planet can go from, in the good case, 1 to 1 million to 1 to 1 billion. Right? And of course, the better your point spec function, so the less light you diffuse, the actually higher your contrast is. So indeed, with that optical quality that the engineers delivered now to us, we are boosting the performance and the capabilities of actually isolated identifying, imaging, and eventually actually taking spectra of exoplanets. As Paul briefly mentioned, it's really enhancing, and it's very hard to quantify yet, but it could be exactly the amount it takes to detect, to characterize a habitable planet versus not doing it. So we're really, really excited about that. And it's, of course, a very prominent science case to actually characterize the solar systems around that, not only our own. And I expect that we have a few dedicated exoplanets missions, but none with the image quality and none with the mirror size of Webb. So that's a field where I think we'll have the most progress in the next few years. Yeah.
Thank you very much.
Thank you. Christian Bank, UMETZ. I actually have 2 questions, and one for the space segment, one for the ground segment. Maybe for the space segment first. You said that the launch was precise enough to save a couple of pounds of fuel, so to extend the lifetime a bit. From an engineering point of view, what would you rank the next couple of life-limiting items? Of course, you may have an assessment. What do you need to pay specific attention to in order not to wear out too early to extend the lifetime, other than the fuel?
Great question. Yeah, we had such a perfect launch insertion and almost 0 tip-off rates that we were ecstatic to see the solar array come out as early as it possibly could. As Markus had mentioned, we were loving it down at the launch site, seeing the images come back from the cameras. We have a really good problem, which is that we're likely not to be limited by fuel. There are moving parts on the telescope. The reaction wheels are things that, we use those to point the observatory. They may be the first thing to wear out. It's funny, you can do these probability of failure, mean time between failure type calculations, and they typically are wrong as far as predictive power go for what's going to wear out first. But there are moving parts. There's the reaction wheels. Each of the instruments has filter mechanisms and other mechanisms in them. Maybe one of those would be the first to go. Who's to know? Hopefully, as Markus said, we'll last a very long time because we're not being serviced, right? This isn't a mission that was really serviceable. We looked at that very early on, and we decided that's not something that makes sense for this observatory. So hopefully we have, our projections are we'll have more than 20 years of fuel lifetime. We're about to do, let's see, tomorrow we're going to do a mid-course maneuver. I'm sorry, not a mid-course maneuver, but a station-keeping maneuver. To stay at L2, which is a metastable point, we need a very small amount of thrust every few weeks. And by a very small amount, I'm talking about something like on the order of 8 centimeters a second of delta V is all we need to stay in our orbit for another, and not need another little squirt of fuel for 3 more weeks. So at the rates we're going with momentum buildup and managing that and station keeping, we're going to have more than 20 years worth of fuel. So we're likely to have that good problem I talked about where something else wears out first. What it is, who knows? But I really hope we're going to get at least that amount of science. The first 5 years are funded of operations, and then it goes through a process at NASA called a senior review for a mission to operate for another chunk of years. And if Webb, the promise of Webb is so high that it's probably safe to say it'll pass senior review as long as it's working. Just like Hubble was intended to be a 10-year mission, and it's going on 32 years next month. So yeah, I think Webb's going to last a long time, and hopefully nothing wears out. Hopefully it just keeps on trucking like Hubble or these Mars rovers and other things do.
I should add that we scientists never let the engineers off the hook. So in fact, as for Hubble, no, they keep working on these missions, and that's what I find so amazing. That as they learn actually the functionalities of the telescopes and of the mechanism, that they keep optimizing them. So we keep actually being able to optimize. I remember that Hubble started with 6 gyros. You need to release 3 to control it, and then they actually, as the gyros failed one after the other, the engineers came back and said like, actually you could pretty operate them with 2 gyros. In fact, actually pretty also with 1. You know what? With 0, it might even work as well. And as like, how long can you actually keep this thing alive? And so what I'm really hoping is that people like Paul and others, will actually do the same on Webb and actually, optimize more and more, also giving us more and more shutter open time, so the time that you can really do science with the instrument. And that's why they'll be working as long as scientists work on the same telescope.
Great.
Paul Antolini, International Press Association. Thank you to all for this beautiful mission that opened up as a golden flower, blooming. So now, how are you going to use all these excellent science data for education? Do we have any specific plan for the next generation or... Voilà, to all 3, Paul, Markus, and Steve. Thank you. And Pascal, eventually.
I must say that it's bringing, it's a new priority, I must say, on the Canadian Space Agency side, that the young and the young to be interested in science. And such mission is very broadcasted very largely into even the young grades, just to inspire them, because it's very inspiring in terms of mission. It shows that when you work together, this is what you can achieve. It's very complex, and as you mentioned, it's very beautiful also. It's not an ugly thing, I must say. Exactly. But we have internal, I'm sure NASA and ESA have the same, we have program to go into school, explain what it is, have exercise, and even some funding, and put their hands also on the data. So this is a new approach that we use. It's not only for astronomy, but we use that for Earth observation and other type of science, space information. And it's working pretty well. We have a junior astronaut program that brings a lot of interest and go in the classroom. So this is part of our mandate now, to develop that young generation and bring them, because that's the future that will use that data for many times. We mentioned that that's the operation of the system that could belong for 30 years, but I'm sure that the data will still be used for 15 more after. So because we'll find new ways to process the data, find new things on the data. So I think that's important to have this. Yeah.
I mean, so I think all three agencies have actually educational programs which are very strong. And one part is the formal education. So the fact that if you look at what was done on Hubble, really exercises which are ready for teachers to download, teacher trainings, going to schools, etc. There's the other part, which is the informal education, in a sense, how much you inspire the next generation to actually go and do science. If you take the people around you, but if I look at my kids and their friends, they all wanted to see the launch of a space telescope. To me, that was just amazing. Just the fact that they actually recognized that was really cool and that they wanted to go in that direction. Okay, one of my daughters is an electrical engineer, so she's maybe more interested in that. She worked for NASA as well. So she was biased, but not the siblings. But that, I mean, the fact that you produce images which are so iconic, like the pillars of creation that I showed you in this optical and infrared, that then hang in classrooms and really inspire the next generation to do science, even if it's not a formal education part. But I think that contributes amazingly to inspiring the next generation to go into science, technology, engineering matters. So, yeah. So I think, to me, that's probably the largest contribution we'll have. And of course, as soon as you come with results which are mind-boggling, for example, if we really found a nearby habitable planet, so what that would produce as inspirational, educational. I think astronomy is often referred to as a science which is very accessible because very visual, and which actually has the potential to drag young kids into STEM professions. Missions like Hubble and Webb, which are really very strong in this imaging, in this very inspiring images, contribute enormously to the education of our children.
Yeah, and all of our respective outreach, public relations people work really well together, and a lot of them are very young and are very media savvy, so they're using social media and other channels, which is wonderful. And just to amplify the inspiration part, I mean, I know I don't look this old, but I remember the Apollo missions. So that inspired me. And even though it wasn't astronomy, that was exploration of the moon. But yeah, I think we can't underestimate the power of just having this stuff out there and people see it and they're just, so curious and so interested and they want to learn more about it. And with the folks we have working in outreach that are really savvy with all the new ways to communicate today, I think it's getting out there. I mean, just last week I went to my local liquor store and I had my Webb logo pullover on, and the guy behind the counter is like, "You work on that?" And he was so excited, and so now I got to give him some pins next time I go in for wine for my wife. So anyway, it's people are hearing about it. It's great. Markus just told me a story where in this your little village in the Alps, and they're all over him because of Webb. So yeah, word's getting out, and we just got to keep doing more of that. And Webb will speak for itself when this stuff first comes out in July.
Yeah, this is actually a wonderful close to the session. We have, I think, 1 minute left. And I want to say STEM education, I think it is really important also for, of course, for the IF. We are really, really trying to foster young professionals and inspiring them for the future, because this is the next generation which has to continue all these large-scale and long-term projects. It's very important, but I think this inspiration, looking really, really deep into the universe, into the young universe, and also looking for eventually habitable planets very, very far beyond our solar system. That is something which fascinates not only young people, but everybody, namely a society at large. And I think that is what we also hope that this telescope will bring, really inspiration for the entire society. And we are looking really, really forward to have great results already on the 18th of September, 18th to 20 September. Actually, the organizers and hosts are also here in this room. I want to really thank this really wonderful panel. I want to thank Steve, Paul, and Markus for this also quite nice portfolio of engineering, science, international cooperation, data science, and please give them a big applause.